Hello, in this video I'll be talking about Python dictionary. Not in a way you probably have seen it before, discussing how to create a dictionary in Python, or how do you access a value using the key, or how do you get all the items, or how do you get all the keys and values. Not in that way. In this video I'll be talking about what goes under the hood whenever you create and manipulate dictionaries in Python. So it's going to be in depth, but it's not going to be convoluted. So I'll be using graphics and easy analogies to make that point very clear. So let's begin. Let's assume we have this very simple dictionary called simple dict. It has 3 keys and 3 values. If you don't know, Python dictionary is a key value pair, right? So we have that, and Python then takes this information and goes to work under the hood, right? Let me just zoom in so that you can see. So the first thing Python does when you have a dictionary like this is it takes all the keys, that is the name, age, and membership in our case, keys here, and then process them through a hashing algorithm. Name, age, and membership will be converted into hash values. I can show you real quick how that happens. So I got the same dictionary here in my Jupyter notebook. So let me take name, for example. So hash of name is this value, right? So that's exactly what's happening now. We're converting keys into hash values, all right? And that's why also hash brown here. So name converts to hash, age the same, and membership the same. Next step, we take these hash values and calculate the modulo of these hash values against the size of our DK indices array. So Python maintains 2 arrays, or hash tables if you want to call them, to enable dictionaries. So dictionaries are known to be very fast and also ordered, starting from Python 3.8, I believe. So we have these 2 arrays under the hood, but in order to put our items into these arrays, Python has to determine where each hash needs to be stored. So to calculate that, what we do is we take the hash value, modulo operator, and the size of our indices array. In this case, our size is 8. So what we're doing is this number modulo 8 produces 2, and the second number modulo 8 produces 4. Third number again produces 4. Now, if you've noticed, what we're saying now is the first number, which is name, it's the green one, right? So it corresponds to name, needs to go to index number 2 in our DK indices array, okay? That is fine because the index number 2 happens to be empty, so we put our value there, which is our hash of the key. Second one, the orange one, which is our age, happens to produce a modulo of 4, which is empty. We put it here. And then the third one, which is our membership, also produces 4. Now here's the problem. We cannot put 2 values in the same slot or in the same index here. So what we need to do is something called open addressing in Python terminology. And that open addressing uses a technique called quadratic probing, which is to say you take the bucket ID, which is 4 in this case, plus I, which is an incremental value that goes from 0 to n, where n is a place we find to put our hash key, right? Hash of the key. So and then we square that, and then we take the modulo of that against the index size. In the DK indices size. That is so that we don't go over the number of indices that we have in our array. Without this, we will be hitting numbers that are not even in our array. So in order to avoid that, we have to take the modulo of that. So here what we're doing is our first attempt 4 plus 0, where I is 0 squared. This will produce 0, which in this case is 4. 4, we've already established that it's occupied, so we ignore that. And then I will increment to 1. So 1 squared is 1. 4 plus 1 is 5. 5 modulo 8 is 5. Therefore, here I said I is 1, and then this is the right spot. So the next value, or the next hash value, goes at index 5. All right? So now we have populated our DK indices array, which is our first hash table, and then the second one. So here it says store key in the store key hash values right here. So the next thing we need to do is we map the occupied indices here into our second array, which is our dk entries array. Okay, so occupied indices are here 2, 4, 5. So 2, 4, 5. Then we basically create an array that's capable of holding objects. This object holds the hash value, the memory reference for our key, the memory reference for our value. So basically the key here is name, right? Name. So name reference goes here. You can find it here at reference 1203, and then the value that corresponds to name, which is John in this case, John goes at 1008. So we're storing the reference and the hash value that corresponds to it. The same goes for 4 and for 5. So now we've created a dictionary from ground up, right? So let's just revise. We have a dictionary here. We take the keys, pass them through the hashing algorithm. We get the hash value, hash brown, and then we take that hash value, calculate the modulo against the size of our array, which happens to be 8 in this case. And if collision is to occur, that is, if two values are to generate two different hash values are to generate two indices that are the same, then we do open addressing or quadratic probing in this case and find the next available spot. Now we'll come back to it, but you might ask, what happens if there are no available spots? First of all, Python has a way to keep that in check. It's called load factor. It's usually 2/3 of these indices, or this array has to be full for Python to go through something called resizing, where it creates a bigger array and starts to copy the available data into the new array, and that happens the same for dk entries as well. But that's a topic we're going to talk about later. But I hope this one is clear for now. So we created our array. Now, the next step we're going to do is, how do we look up value by key, right? For example, if we want to get the value John in Python, it's quite easy. What we need to do is simple dict square bracket, right? Quote unquote name, close square bracket. That should produce John. But now let's go and learn how that happens under the hood. All right, let's open our visualization here. There we go. So we have the same dictionary, but in this case, we're not creating a dictionary, we're looking up the dictionary to find the value gold, right? So what we're doing in Python is simple dict membership, right? So what we do is exactly the same thing. We take the membership, which is our key, pass it through our hashing algorithm to produce a hash value, right? Here, let me just zoom in a little bit so it's visible. Then we will calculate the modulo of this value to determine where to look, right? So the modulo, we've talked about the modulo operation earlier. So it produces 4. That means our value resides at index 4. We go and look for index 4 and try to match what we got here, which starts with -3. But what we got at index 4 is a value that doesn't start, or it's not the same value. That means collision had occurred at the creation time, and quadratic probing had happened and placed the value we're looking for at the different slots. So we have to find it. In order to find it, what we do is exactly the same. We do the same quadratic probing, which is we take the bucket ID, which is 4 plus 1 squared modulo 8 produces 5. So we go to 5 and check whether the value at index 5 matches the value we produced while hashing, and it does match, right? That means we found our slot. So then, because we know that the indices in the dk indices array are mirror of dk entries array, we just jump to directly index number 5 at dk entries array, and then we look for the memory references and we take it from there. So basically here, what we're doing is check if the hash value at index 5 matches the hash value at the same index in the dk indices table. We check that and they do match. If true, then we're going to read the value based on the memory reference and return it. So basically here we have, this one is the memory reference for the key, memory reference for value. We've seen that earlier. So based on this memory reference, we go to the memory, read that value and return it. Now here, what we're doing is do quadratic probing, find another slot where both hash values match. So sometimes could happen that we come to 5, but the value is not here. So we do the same quadratic probing and then return the value. If we can get here sometimes and we can do quadratic probing and we can't find it, or we hit a blank spot, in that case we return key error. That means the key that we're searching for is not here, so we return key error. So basically this is how we look up value in Python, and this is what goes on under the hood. The next one is to see how deletion works whenever we delete a value in Python. How does it work in Python dictionary? Sorry. So here we got the same dictionary. We're doing dictionary name pop and the key value pair, the key we want to pop or remove in our case. So we want to remove a name and John, so that our dictionary will be remaining as age 34 and membership gold, right? To do that, we go through the same similar process, not entirely the same. So we take name, hash it, get the hash value, and then in order to find where name is located, we have to do modulo calculation. We do that, and our calculation spit out 2. We find 2, and then here is a tricky part actually, what I found quite fascinating. We do not delete values immediately in Python dictionary hash tables. What we do instead is we mark them as kind of temporarily occupied. That's marked in CPython as DKIX underscore dummy, or it could be a sentinel that's like -1 to indicate that this is not empty but also doesn't have value at the same time. This is to increase efficiency, and you can ask questions like, oh, if we keep filling up values like this, then at what point do we delete them? And I'll answer that in the next section when we look up resizing. When we look at resizing. So here we marked this index 2 as dummy or temporarily occupied, right? And then we jump, as we said earlier, these two tables are mirrored, so we just jump to exactly the same index table in the DK entries table, and then we mark these 3 values, or index number 2 as DKIX dummy as well, indicating it is not empty, but it also doesn't have an applicable value or an actual value. So it usually sets the object null for each attribute. And then we go further, find the references in the memory, which is John and name, and we clear them. We don't care about what happens in the memory. What we care about is not to delete values on these tables or on these hash tables immediately. Thereby, later on when we check for values or when we do quadratic probing, there will be an early stoppage, which we don't want. So if it's empty here and we're searching to find a spot that actually exists, but we hit this empty value, it stops. The algorithm will stop thinking we hit the wall. So we don't want that. That's why we keep them as dummy values. So basically this is how we delete values in Python, but we don't actually delete them. We only delete them from the memory, but the tables keep them as dummy values. And when we look at the next section, which is resizing the table, you will understand why that's the case and how do we purge them as well. So moving on to the next slide. All right, Python dictionary resize. Here is where we discuss resizing. I touched on it a little bit earlier when I was talking about the load factor. Here I'm assuming now we have a bigger dictionary. Okay, this dictionary has about 7 items, one of which we happen to delete, which is the country one, and the rest 5 are there, therefore leaving us with 2. Now this dictionary by Python's book has reached load factor, which is to say the number of items divided by the array size is close to, let's say, 70% or 2/3 is occupied, right? That means we need to find a solution there, so that we don't run out of rooms to place hash keys, right? So in order to do that, Python usually doubles the size of the initial array. So here we have 8, so we double into 16 here, and then what it starts to do is copy these values into the new index into the new array that we just created. Okay, so and this is where it starts to look at each value. It starts to look at each value and does what we have done earlier, which is do the modulo operation. Why do we need to do that? Because the size has changed. And if you remember, our denominator earlier was the size of the array. So that means now our values will be stored at a different index than they were before, because the size has changed, right? So we iterate through each of them and find them new homes in the new indices array. While doing that, we're also checking whether each hash value is what's the right term here? An actual hash value. Therefore, our deleted items that we marked as dkix underscore dummy or -1 are not considered in this process. So this is our opportunity to clean up our table as well, not only to expand it. So we ignore this and copy the rest of them here. I haven't actually done the calculation here, as in I haven't done the slash modulo 5. Sorry, slash we haven't done the modulo 15 here. So you might say like, why is 1 mapped to 1 and 3 to 3? That's just just to visualize. It doesn't actually represent what goes under the hood with the actual 15 value. So just use your imagination there, or you can even take these values and calculate the hash and do the modulo, and you'll find the actual value. But this is just for demonstration, yeah. So some notes here. So we're recalculating the modulo value. Hash value, the new size, gives us the new index, or where we should put each hash value from the old table. And then I also remarked here saying dkix underscore dummy values will be ignored during this process, thereby giving us a cleaner dk indices table. The next step is Python then populates them. This is our new populated dk indices hash table. Now we also have to do the same thing for our dk entries table. Let me just zoom out a little bit here. This is our old one, and in this old one as well we have 5 items and 1 deleted, which is the country key we deleted earlier. Now this usually doesn't happen, like only 1 is left, doesn't happen, so don't take it as well literally. It's just a figurative representation. So here as well we do the copy. We copy each item into the new table. We don't do hashing here. We just map them to the existing as per the existing dk indices table. But while we do that, we also cross-check every item to make sure that it's a valuable, or not valuable, it's an applicable value. Therefore we will ignore this item here, dkix dummy entries. And that's all. This is how Python works under the hood whenever you manipulate dictionaries. We have covered how resizing happens, but we talked about load factor, which is to determine whether to create new hash tables, and it's usually 2/3 or 70% of the indices must be occupied before we do table resizing. While resizing, we ignore indices that hold dummy values. And we talked about quadratic probing right here when we start. We talked about it here when we find an item. We also talked about quadratic probing while creating a dictionary from scratch. And we also talked about deleting and how it marks indices as dkix dummy, or it will give them like -1, and how we delete values from memory, but we don't delete from dk entries and dk indices, and that's for efficiency reasons. That's all. I hope you now have a better understanding of Python and what it does under the hood, and thanks for watching.